in the previous chapter, we developed the natural numbers, and the method was just looking for the successor of each natural number by looking at them as the union of two sets. The problem for that was like it's too complicated, and as you can see in the homework problem, just looking for m plus n, it's too much work, right? If you really want to show one by one. So in this chapter, we are going to develop the new way of defining integers. Of course, the meaning of number 1, 2, 3, the natural numbers, we need that to develop natural number systems, right? So don't lose those concepts like 1, 2, 3, the natural numbers, which we developed in the previous chapter, right? But from now on, we are not looking those numbers in that kind of set notation kind of anymore. Okay? Like we're assuming we already did it and we knew about it, right? We know the whole thing, so we are not digging into that way. So from now on, we are going to use that natural symbols of these natural numbers as it is. Okay? But still, we don't know how to calculate the subtraction yet. Okay, so let's develop the whole thing. One of the big thing about the natural number set was those two operations are closed, which means when you're adding up two natural numbers, it must be a member of the natural number set again, right? Because the meaning of this is what? We are looking for just n successor of m, right? We can translate that way. And how about the multiplication? That's m plus m plus m, right? N times, like that. So we are looking for m's successor of m and m successor of that number, m successor of that number. We are looking for n times what, right? So these two operations in this system, we just treat them like looking for successor. Okay, that's a specific point. Okay. Now, that's too complicated, right? So we want to develop a new way of that. And the problem for the previous system was, okay, we don't know how to handle that, right? Predecessor, okay, but remember the piano's axiom says there is no predecessor of 1. So how can you find that? How about 8 minus 7? I mean, that is still okay. How about 7 minus 4? What is, that's still okay. 4 minus 7, sorry. So even this is okay. We can understand like a fourth predecessor of number 7. But how about 7's predecessor of 4? There is no such number. Now, so the meaning is that number system is not enough handling those operations, right? So we are in big need of having some more numbers. Now the problem is, how can he explain meaning of negative 3, right? So do you remember in elementary school we explained like, yeah, I borrowed three apples from you, and all the kind of concepts of this borrowing and giving and take. It's kind of one way of explanation, but it's not really the explanation of it, right? So mathematically, we need more rigorous explanation and definition of it. Okay, so you're going to feel like this one. Whenever we're dealing with some concept in math, it looks like so complicated because the only reason for that is we are not getting used to see that way. But after you have enough practice, you realize why mathematicians make those rules that much complicated. Because it's actually the easiest way to understand it and developing the skill, the whole systems, and even for kind of some calculations if it's needed. Okay? So you are going to see that here. So please follow me. We want to make a new set. Let's just say it's just capital X. It's a collection of ordered pairs of natural numbers. So if it's ordered set, we always kind of use its Cartesian product notation, okay? And by N. So which means the set X is just a collection of, let's say these are natural number set. X is another natural number set, comes with number 1, 2, 3, 4. Keep doing it. And number 1, 2, 3, 4. Okay, keep doing it. Then these grid points will denote each ordered pair, okay, in this Cartesian product system. So we have name of this. For example, this one should be 1, 1, right? And that should be 3, 1, right? But that is 1, 3, right? So like that. So X is just a collection of those points, these grid points. We can think that way, right? And each single element in it can be written by n by n, right? So that's the whole kind of condition right now we have. Now, we want to give a relation on this set. Giving a relation means you can collecting those elements which are related each other together, right? So everything depends on how we are going to give that relation, right? What is the relation right here? You can give anything you want, but in this case, we are seeing these two elements in this set X are related, okay? And when you can say that, if this equation is satisfied. So we are going to adding cross y, right? Cross addition. You could think that way. So this one plus that equals this one plus that. Then it turns out that this kind of relation take a partition of this entire set into disjoint subsets. So let's look at this one. This X can be separated into several, actually infinitely many sets, okay? But for better notation, instead of just saying 1, 2, I can put S of 1, 1 union S of 1, 2 and keep doing it, and something more, okay? And even S of 2, 1 and even something more like a 7, 4, okay? If you want, you can imagine like that, right? So let's look at what is each individual subset has, right? Like what elements is in each, right? And for example, S11 is a collection of elements from X which has relation to 1, 1. And what type of elements has a relation with 1, 1? So let's check. Mn has a relation with 1, 1. Then by the definition, whenever we say that, it must satisfy this one. So m plus 1, right, must be equal to n plus 1. Then it turns out that it's m equals n, right? I have to cancel out that. So any elements in set X, those two, let me say xy coordinates, right, are equal. Then we know that it's 1, 1, 2, 2, 3, 3, 4, 4, right? So let's just collect those elements all together. Then the name of this set is going to be S11, right? Right? Okay, then how about S sub 1, 2? Okay, for this case, if we have any elements related to 1, 2, okay, we are collecting those, then m plus 2 equals n plus 1, which means m plus 1 equals n. So meaning is the y coordinate must be successor of the x coordinates. So which ones are those? Like 1, 2, right, as in here, and 2, 3, 3, 4, those numbers, right? So where it is? 1, 2 is here, right? And 2, 3 is here, and 3, 4 is here, right? So, oh, it's nicely arranged even like this, right? When you collect those, And the name of that is S sub 1, 2. Okay, so when you look at this, we could find some kind of pattern here, right? Okay, so if it's like, let me say 1, 7, then eventually we are going to have m plus 6 equals n, right? And that entire set must be placed and starting from 1, 7, right? And collecting all this, right? So that will be S sub 1, 7. So when you look at this whole thing in this way, then eventually in this grid point system, like a Cartesian coordinate system style, we know these are S1, 1, that is S1, 2, that is S1, 3, right? And keep doing. So if it's arbitrary n case, this set will be written by S sub 1, n, right? Okay, then it only take care of kind of half of this entire grid point system, right? We have about half of them left over. So when you look at those, what is going to be name of that? The starting point is 2, 1, right? And that is 3, 1, right? Okay, so it's going to be, after we have collecting all this, we are going to have really nice kind of partition of entire X. And each subset for that looks like having those numbers, right? Then the question is, I gave this one, just randomly I chose it, right, over there. What does that mean? Because when we have those partitions, we always use the order pairs of this kind of first points, right, in each group, right, close to that x-axis or y-axis, right? But 7, 4 means 1, 2, 3, 4, 5, 6, 7, and 1, 2, 3, 4 is around here, right? So how can you get S sub 7, 4? Is it possible? Yes, that's the power of equivalence class. We're not going to prove it, but this collection of S sub something, right, like m, n, okay? And you could say these m, n's are just any natural numbers. This notation is still possible, but its equivalence class means we just denote that one as a bracket around it. It's nice disjoint union of disjoint subsets of this entire element. Okay? So look at where this coordinate, the order pair belongs to. 7, 4. Okay? Then when you start from 3, 1, the next one is 4, 2, right? And next one is 5, 3. Next one is 6, 4. Okay, it should be about 3 different, sorry. So it must be starting from 4, 1. Okay. So 4, 1. Then that one containing 5, 2. So 4, 1. The next one is 5, 2. So increase just 1 for x coordinates, y coordinates together. So 6, 3, and it's going to hit 7, 4, right? So that 7, 4 belong in this subset. So if we just say 4, 1, then they are just the exact same set that we are talking about, right? So still it's okay if you understand how to get, right, which one belongs to which. We are going to talk about the next subset, but next subsection, right? But so when we write down those numbers, we are not saying those numbers should be used, right? Should be used in there. No, it's not like that. You can choose something else if they belongs to the same subset, which means they are actually has that relation, right? Okay, we are going to show that one later. Okay. So those index, like let me say m comma n, it's just representative of those subset, and which number is going to be the one doesn't matter. Just choose anything, any elements, and use the elements for that index of that set. It's still okay, but maybe it's better, right, using this initial. So usually this is going to be s sub 1 comma n or s sub m comma 1, right? Because those ordered pairs are the closest one to x-axis or y-axis, right? Most likely. So this is easier just for us. That's all. But no one says we have to use these ordered pairs. It's okay, right? If you use something else. And the only reason for that is because this relation is equivalence relation, and the entire x can be written by this union of these equivalence relations, right? So then what do we have to use this letter s to denote it? No. How about just 4 comma 1 at ordered pairs? Good. But 4 comma 1 is just only a point, right? But how about the entire set, especially the equivalence classes, right? Then we just put the bracket around it, and that is the notation for this set. Okay, I don't know how many of you already had that experience before, but then why do we need this stuff? Any elements belong to one equivalence classes have same property, and that same property is very useful for us to calculate in much simpler way. So instead of 7 comma 4 and do some operation with 101 comma 49, whatever, right? Whatever we define for that star operation, instead of this, we can looking for the representative of this, right? So like this 4 comma 1, then we are going to have the representative of this one somehow, right? Then this is one of the example. Like we can reduce this big number into much smaller number, and that operation is really easier than handling this one directly, right? More important reason for that is because of this, no matter which element we choose from each equivalence class, we will get same result. So it's like this. We just choose this set and that set and do some operation about it. We just pick any random numbers from this and do that operation individually and got certain results. And we know that belong in this group, this subset. That means we just choose, doesn't matter which one we choose, right? From these two groups, the results is always landing on here. Okay? So as a big picture, why do we care about that individual cases, right? Let's treat this one as just one object, okay? One number, okay? Whatever, and that is another number, and do that operation is always that number, right? That's the whole concept. Okay? And because of this, in math, we really could handle big things in very simple way. And one of them is using this prime factorization, right? And handling those remainders, and that is one example is really helping us to develop all this cryptography and the security system online such that, right? Okay, so that's the main reason we're very interesting about it, and we also use that same kind of concept to developing this integer concept.